All right, guys. So today I'm going to do a few different things that are somehow disconnected, but for the most part it's responding to some questions. The first one, I posted this on Canvas, but I wanted to show it to everybody and have it on video. There was a question about, is it possible to obtain orbits where the Earth, the Sun, and the spacecraft are basically stationary with respect to each other, and maybe you see the Sun all the time? Well, that's the multi-body problem, where you only have Sun and the Earth, for example. I don't know if we'll cover this. I don't usually go through the math of Lagrangian points, because that's usually advanced astro or graduate level astrodynamics. We'll see. But just for your knowledge, if you consider a satellite and the attraction of now Sun and Earth combined, which we're not going to, again, do probably, for us, we'll transition from what we'll call the sphere of influence of the Earth. We assume that we exit that and the Earth disappears, and then we are under the influence of the Sun. That's what we'll do for interplanetary travel. But if you do keep them into account at the same time, which is more realistic, and if you define a coordinate system that has one axis aligned always with Sun and the Earth, there are, as you can see, 5 points that are equilibrium points, also called Lagrangian points, where if you put your satellite there, in principle, it will stay there in these coordinate systems. So it doesn't matter if the Earth is rotating what it's doing around the Sun. It will be always, for example, at L5 or L4 or L1. And so from there, you can definitely see the Sun at all times. The James Webb Telescope instead is going to use this one behind, if you want to call this behind the Earth on the other side, which is L2. It's going to orbit close to that point. And so some of these are stable, some are not stable. If I remember correctly, these two are not. This is not. This is, otherwise you wouldn't put it there. And the other ones are stable too, meaning if you give a little perturbation, the satellite will not drift away without coming back. But that's the answer to the question. Yeah, there are some equilibrium conditions where you can be exploiting the action of Sun and Earth at the same time. So there was a question about this. Again, I don't know if we'll see the math for this, but that's what they're called. And Patrick, for example, is studying Lagrangian points around Mars, including the Moon and Mars. So you can scale it to whatever is your interest. In this case, all of these points are, if I remember correctly, the closest is 1.5 millions of kilometers away from the Earth. Should double check the exact numbers, but they're all outside what we will call the sphere of influence of the planet. So they are pretty far from the planet. It's going to be a stretch to actually call, to talk about orbits around Earth in that case. You really are looking at more bodies that are attracting your satellite at the same time. So we'll see this flying pretty soon, pretty far away from the Earth. So that's the response to that question. Then there was another one about the delta V's, and I actually gave you some kind of uncollected homework, if you like. Last time I said basically that the following expression, when you use an engine, the variation of mass, because you are turning on an engine over the initial mass of the spacecraft, is given by 1 minus e exponential of minus delta V over the ISP times acceleration of gravity at sea level, right? And I gave you an exercise. We solved an exercise where there were 2 burns. And so I have used this formula, and I basically took this delta V and I just added the magnitudes of the delta V's, right? That's what I've done. And if you plug in the numbers with an ISP of 300 seconds, if I remember correctly, for that particular transfer that we were looking at from an ellipse to another, this ratio was 0.64 something, meaning using 60% of the fuel. Now, I understand that many of you may be disgusted by that number, but that's what it is. You do use more than half of your weight for that maneuver. And so if you want to prove to yourself that you can use this formula once and for all, so this is the mass of your spacecraft at the beginning, and this is the total loss. It doesn't matter if you turn on one engine, then you wait, you turn on the next one. You can do it easily the following way. If you do the first burn, what do? You create a delta M1, that's the mass you lose because you turn on your engine, over the very first mass of your spacecraft, the very initial one, whatever that was. I think it was 2 tons for us. That's going to be equal to 1 minus E to the minus delta V1 over ISP G0, okay? And then you can do for the second burn that delta M2 over what now? You are supposed to solve these by yourself. It's not really a big deal, but it's a good exercise. So if this is what happened at first burn, then I use this mass, I lose it. So my new starting mass is M0 minus that, right? And I create a delta M2, 1 minus E to the minus delta V2 ISP dot G0. So since I don't like this ugliness here, I'm going to call this X1, except the minus maybe. And call this X2 for simplicity. So let's, what I want to do is prove that I can get to this expression. I can just forget about doing intermediate steps and just plug in the addition of all the delta V's in here and get the final delta M, which in other words is delta M1 plus delta M2, and this has to be M0. I want to prove, starting from these two formulas, that these holds. Make sense? That was the question I had the last time. Well, you start from this one. Delta M2 is equal to, I don't know if I want to shut off the projector. Yeah, no. Is M0 minus delta M1 that multiplies 1 minus E to the minus, what did I call that, X2. Okay? Now I take the delta M1 from this one, and it gives me the following, M0 minus M0 that multiplies 1 minus E to the minus X1, and the whole thing multiplies 1 minus E to the minus X2. Okay? Keep going. Let's see what we get. What did I do? Multiply this times this. You get M0, 1 minus E to the minus X2. And then minus M0. Oh, it's not going to fit in here. 1 minus E to the minus X1. Yeah, maybe. Can you see it? M0 times this is this piece. This whole thing times this is this piece. Okay? Let's clean it up. M0, 1 minus E to the minus X2 minus, let's do that product in there. Let's see what we have. 1 minus E to the minus X1 minus E to the minus X2, and the product of these exponentials, which is plus E to the minus X1 plus X2, right? You see that? Agree? All right. Collect M0. I get, well, 1 minus 1. And then I have minus E to the minus X2 minus, I'm sorry, this is a plus actually, because I'm changing the sign here, right? Well, no. This has the minus. That one has the plus. Anyways, they go away, okay? Plus E to the minus X1 minus E to the minus X1 plus X2. Okay? These disappear, these goes away. Bless you. I am left with M0 that multiplies E to the minus X1 minus E to the minus x1 plus x2. Okay? And I really don't want to bring that up. I'm going to erase this. This is still calculating delta M2, right? So delta M, which is delta M1 plus delta M2, is going to be, well, delta M1 is this expression here, right? And delta M2 is that. Minus e to the minus x1 plus x2, which finally, this goes away, gives me m0 that multiplies 1 minus e to the minus x1 plus x2, which is exactly what I wanted to prove. If you want, divide by m0 both sides, you get the left-hand side of these parentheses e to the minus 1 minus e to the minus everything is equivalent to this. Settled? Can we agree on this? You can do it with 3, you can do it with 4, it's just the same kind of process. So if you burn an engine 1,000,000 times, add all the magnitudes of delta V, you can use that formula to give an estimate. If you know the ISP, of course, of the engine, add all the delta V's together. This gives you an estimate of how much fuel you're consuming. Any more questions on these? So I'm sorry, for the bad news, is 64% of your mass used for that maneuver. Yes?
Now, if you did like different boosts with different engines, you have to have that.
Yeah, that, then you can't do this nice exercise. Well, yeah, no, because yeah, I can't. Since the denominator of this remains the same, I could do this procedure that I follow. Yeah. Then you will have to do it by steps, but yeah. But here I was using the same engine. So yeah, that's a simple expression that gives you an estimate. Okay, so that is for that problem. What else did I want to tell you? I think I made a comment last time. There was another question about can I just make engines more basically efficient by ejecting more mass at highest speeds? And again, the response is if you set the amount of mass you want to expel, then the velocity of exit at the nozzle is something that will be limited by the technology. If you go back to your propulsion class, there is a component of the thrust that is given by m dot, the product with velocity, and there is another piece that is that has to do with difference of pressure. But at the end of the day, you can't really change those numbers the way you want because of limits on materials, limits on how you can cool the nozzle. Have you ever been to Kennedy Space Center? Have you seen the shuttle there? Have you seen the video that they have at the beginning to introduce the shuttle, which is pretty cool? So one of the very first formulas that actually appears on that video is the thrust formula. So pay attention to that next time. It's there. They project it on the screen. And so there is that term that has to do with the mass you eject and the velocity of the gases. Technology progresses, you can do more, but it's not something you can choose randomly. Again, there is always a trade-off. Now, any more questions on these topics? I was supposed to go ahead with more impulsive maneuvers, but I want to do something else. Maybe we'll still talk about maneuvers, but first, I want to reproduce this homework too, basically, from last year, this ground track exercise with STK. Have you tried to do this? Nope, not at all. Let's try this. Okay, this is what I was getting by rerunning this code, and hopefully I haven't changed any of the constants, and it still works. Of course it doesn't. What is it doing? Okay, works. This was, the one plot that I want to reproduce is this one. I want to show you that not only we predicted the right time to see the ISS, this kind of plot is what you get from STK as well. So I'm going to close all these for now. And I think it's time to talk STK in class. It's not something that I'll dedicate lectures to, too many other than today. But it is a good point now that we're doing more serious stuff, ground tracks, maneuvers. It is a good tool to play with, and also to verify your simulations. Okay. So I have not even 20 people who sent me level 1. So I'm assuming that all this stuff sounds still pretty new to many of you. I don't know, but let's do this. What do we call it? We call it ISS Ground Track, and you guys can help me with this. So you open STK, you're going to create a virtual world here with the planet and your satellite. That's what I want to do. And it starts, does it already have the right date? It's today, right? But in MATLAB, I had a different day. This one. It's the 15th of February, right? Is that what we said? That was the 15th of February. Because it's the 46th day from the beginning of the year, 31, 15, yeah. Do you have any questions? 15th. And we start at noon, and this universal time does basically match the GMT. You can convince yourself about that. Reading the STK helps. So what I am going to basically do in STK is simulate for an entire day, which is what I've done, right? One day, starting from these orbital parameters that I'm going to enter manually in STK, starting from the 15th of February, 2017 and noon. Okay, ISS Ground Track. And I hope I don't have a scenario with that name already. It's going to disappear on you and eventually open again. It's not responding. It will, I hope. Okay. All right, so it's asking me to add something. There's just the planet for now. There's no vehicle moving. There's no location on the planet. There's nothing. So this is the object browser. And I'm going to enter a satellite. You could download the ISS from online databases. I'm not going to do that because I am afraid that I'm going to make a mistake with the time. So I am actually going to enter the orbital parameters that I have one by one, which means I'm going to open the Orbit Wizard, which allows you to basically select those numbers by yourself. Now here you have different options. Known, you see sun synchronous is here, geosynchronous. I don't want any of these. I want to design my orbit. And here I have to, unfortunately, copy-paste these numbers, probably. Okay, this is the same image or axis, right? Is this interesting? Yes? Okay. Now, that's in kilometers. So that means I have to move 1, 2, 3, right? Right here. Oh, no. What did I do? I entered the satellite already. Okay. That's fine. Close these, open these. I'm basically not done editing my satellite. Okay, satellite 2 is something that I entered by mistake. So orbit, okay, semi-major axis is there. I think that's the only one I entered, right? 6, 7, 8, yeah, that's the one. Eccentricity, need to change that. I don't know why it shows this way. I think it's my screen's resolution. Let me try to change that. Hopefully the projector is not going to explode. I don't know why it does this all the time. How many love Windows 10?
I love Windows 10.
You do?
Oh, yeah,
You're fired. You are fired. I don't like it. It plays. See, the resolution is less. I don't know why it's. Is it going to still project if I do this? I don't think so. Let's try. No. It's worse, right? It's cutting some of the names. Do we care? We don't care. I'll go back to these and keep going. All right. So I was at eccentricity, right? All right. 0 point, whatever the number is. Inclination in degrees. I don't think I need it in radians. I think it takes it in degrees. Here it is. And then ran. I know this is boring. It's like watching someone doing a tutorial, but that's how it is. Argument of perigee. Right here. We're almost there. Is that the argument of perigee I just copied? I hope so. Yes. Ran. Did I do ran already? Yes. Okay, I was almost done. True anomaly. And we are done. Okay. Notice up here, even if it's barely visible, it's terrible. You can choose different orbital propagators. I am using here the two-body, which means r double dot equals minus mu over r cubed r, nothing else. You can have more elaborate ones if you could only read what it says there, but more or less you can imagine that's J2 perturbation, J4, SGP4, there's different orbital propagators that you can use. High fidelity, HPOP is the high fidelity one, but let's do this for now. So hopefully this is the right initial condition for the ISS. And you have the 3D view, you have the 2D view with the ground track. I'm going to add something else. I'm going to add Gainesville, which is a place from city database. Should be able to actually search it in this terrible screen. I need to do something about it. Florida, do you see it? Yeah, I don't either. I think that's the one. Okay, we're not done changing the resolution. I'm going to try again. It's reducing it that should work, right? You would assume so. You don't know how many times I have emailed the AGI about this thing. Their response is, we don't know. It's your computer, it's your fault. No, I'm serious. Makes it worse. Oh, okay.
That's a little better.
No, it's cutting all the names. See these? It's just the windows don't... How about this? Brute force solution. Okay, it went back to recommended for this screen. And let's see what it does. This is what it thinks it's the best. Anyways, Gainesville should be there. Yes, it is. So let's see if we can run these. And so remember, this is the timeline down here. Do you see it moving? You can see what time it is. It's still the 15th of February 2017. So it resets the ground track every orbit. And I think we had a pass over Gainesville that was visible at night. So of course, whatever will happen will have to be when that dark is over Gainesville. And it was, what time was that? 8 p.m. for us, which GMT time, which is what we have down there, was already 1 a.m. of the 16th, right? 8, yeah, 5 hours, yeah. So it's getting there. I can speed this up. I don't want to. I want that pass to be clear. And if you actually go online and check, also, you can see images of the ground track, how it's coming above your head. It's coming from north. That pass was the ISS coming from Georgia, and we could see it. It's just to visualize. Then we're going to actually pull out longitude and latitude from STK and compare to what we created in MATLAB. It's getting there. You see the dark coming over? Yeah, it's the end. Almost. Not this one. I don't think so. Yeah, midnight, the next one. So the next one is your pass. Here it is. It's about 1 a.m. in London, and that's when we could see it. Okay. But yeah, this is just, nice images, visualizing stuff in 3D or 2D. Let's try to actually extract some numbers. Why do I have another satellite? Oh, that's the satellite. Gainesville 1. I don't need Gainesville 1. So you can create reports, right? In STK, those of you who have done STK certification, at least first level, may have seen that. I'm going to remove this one that I created yesterday, just to practice this. I'm going to create a custom report, basically data, that includes only, what do I want? Longitude and latitude, right? I'm going to call it Ground Track again, even though I just removed it. So you click on it, and you decide what I'm going to move on the report contents is whatever variables I want. There is so much stuff you can choose that it will drive you insane. But we do know what we want. It's longitude and latitude, and that belongs to this category here, LLA, longitude, latitude, altitude, fixed with the planet. But I'm going to just pull this one, longitude and latitude, nothing else. And I have created my custom type of report, so I can generate now the report. Here it is. So this is just creating every 60 seconds. I think that's my time step. You cannot see it. I think that's the default. You can change it. It's giving me a longitude and a latitude. Now the difference with what I've done in MATLAB that I showed you, I went with longitude from 0 to 360. This is going minus pi to pi. You can always modify that. Latitude is going to be minus 90 to 90. So what do I want to do with this? I want to see if plotting this into the Mercator plane is going to match what I have created in MATLAB, right? So there are many ways you can do it. The way that I'm going to do it, because it's brute force and I don't want to waste time, is I'm going to create an Excel file. I'm going to copy the values in MATLAB and use them. I know you can read from Excel files. That's fine. That's not what I want to do. I think I was already in the right folder, right? No. Where do I save it? It doesn't matter. Desktop. Save. Okay. Is it there? I hope it's there. Here it is. Okay. So I have longitude column, latitude column. The brute force approach that I'm going to use is the following. Delete. I'm going to copy this. Remember, this is longitude, right? I'm going to go in MATLAB. I think I want to erase this one and this one. Clear my desktop, my workspace. Nope. Okay. Let's see. Longitude. I'm just going to define a variable, right? Is equal to. I'm going to create it with a 1. Then I go in. I mean, this is very bad practices. So this is just because I need it to work quickly. I just copy everything in there. Okay. That's my first variable, and it contains all that data. Then the other one is latitude. I'm going to do the same thing. Copy. Paste it. And call it a day. And then I'm going to save these. When you do this, you just save longitude and latitude. I just have everything saved into a .mat file that contains the two variables. Now, with this simple function, what I'm going to do is load that same file. So basically, I'm going to have the longitude and latitude vectors. This instruction is going to take the longitude that is minus pi to pi and just move it to, well, minus 180 to 180, just move it to the range 0, 360. Simple mod instruction. And then I'm going to plot that, and hopefully it makes some sense compared to what I had before. Okay, bunch of points. Did you know, you probably know this, that you can take plots and move them around? You knew this, right? Okay. I'm not suggesting that you should use it as a common practice, but so I copied that plot actually. I copied that set of points, and I want to overlap it to this one that I recreated from MATLAB. So this was the ground station I created with my code. If I copy, why doesn't this go away? Go away. It doesn't go away. If I copy the ground station points in here, it's kind of okay, right? Do you see that? Do you like the comparison? You think this is acceptable? They seem close, right? But to me, the planet is big. I don't know how many degrees this is. I can probably figure it out looking here. Maybe it's 1 degree. 1 degree is a lot. There's something that creates a difference. Yeah, they're kind of going together. It is a good validation of my code. It's making sense, but they're not on top of each other. Why do you think that is? What have I done in STK that, what have I not done in STK that I was doing actually in MATLAB? J2 is not there. J2 is terrible. So apply J2, rerun your, I'm going to close this, redo the ugliness of creating this report in Excel if you want. Yeah, overwrite it. I don't care. I'm just going to copy the numbers. Well, you know, just to be safe, let me close this. No. Save it again, because I don't know where it went. Yes. Okay. Now I'm going to reopen it. Hopefully the numbers have changed enough so that the J2 makes the plots match. What do I do? I'm going to load these. I'm going to hack the variables, right? Overwrite the numbers. Control C, Control V. That was longitude. This is latitude. Is everybody following? Is this making sense? Is this interesting? So, and hopefully this contains now the right data. I'm going to save it. Run this again. Copy these points. I don't know how. It's not selecting them. Thank you. Color, just different color, red. And go back to the ground track I was creating before. Much better. Can you see the red dots? J2 does that to your orbit if you ignore it. And again, 1 degree on this map is, I don't know, many kilometers on the ground. So the previous one, you can do the math, 1 degree in radians times the radius of the planet. You can do that math. It's probably not very acceptable, what I was showing you before. But just adding J2 makes a lot of difference, as you can see. So we are actually using MATLAB to do pretty serious stuff that a commercial software can actually do for you, which is interesting, no? Any questions on this? All right, next one. The next one in STK is, I don't even need MATLAB now, is what we have seen last time, and is the Hohmann transfer. So if you actually, I don't think I need to, okay, save this. I think I can close the Excel. So how many have heard of Astrogator? It's a piece of STK that allows you to solve for maneuvers. For example, it's a numerical solver that will find you a maneuver to go from an orbit to another when there is no analytical solution. Now, for Hohmann transfer, which is what we discussed last time, for example, small circle to big circle with 2 impulses, it's pretty simple, right? We just have the 2 delta V's that you can compute on a piece of paper. But the exercise that you can find online, really what I've done is I printed out what they do online, makes you calculate those delta V's in an iterative fashion, just as an exercise to get familiar with Astrogator. But the reason why I want to at least start it here and then maybe you finish it if you have time, is that for those who are in the aerospace design class next semester, if I am the one teaching it again, we've used Astrogator pretty heavily to solve for actually continuous maneuvers with small thrusters, with CubeSats. So it's a pretty powerful tool. It's numerical, so you have to set it up the right way so that it eventually gives you a meaningful solution, which it doesn't usually do the first time, except for very simple problems, but it's a very powerful one. So again, this you can find it online. So I'm just going to follow these directions written in extremely small text. I'm going to design a Hohmann transfer that goes from a parking orbit of 6,700 kilometers to an outer orbit of 42,000, I think is geostationary type of orbit. Okay, so let's see what they have us do. Create scenario, let's call it Hohmann transfer. Do they have preferred dates? Yeah, let's do what they have, why not? July 1st, 2016 at 4 p.m. and it's going to last for 2 days. You can interrupt me anytime if something is not clear, of course. 3 days, no, 2 days, sorry. I think that's all. Okay. It's going to create the planet. Okay. I'm going to introduce a satellite again. Let's see how it has you doing that. I think I just define properties. I think that's the quickest way to get there. So this will open the page of the properties of the satellite. So here you can actually select, even though you can barely see it, now that I have the mouse on it probably, you're going to say that you use Astrogator, which means this satellite is something you put into your scenario because you want to solve for something numerically, okay? And that means you have to create a sequence of, here it is. We have to populate this area here, which is called MCS, Mission Control Sequence, where you have to tell the numerical solver what it is that you want to solve for. In this case, it will be 2 types of maneuvers. All right, so we say that we define an initial state that's already there with a radius of 6,700 kilometers. Okay. And that's the, you can call these, just to make it more meaningful, the inner orbit. We're going from a smaller orbit to a bigger one. So this is your start. The Cartesian coordinates, we don't like them. We like Keplerian. Here it is. This is 6700, and the rest we are told it's all 0. That's it. And I believe that's it. So that is my initial state. I start from a circular orbit with that same major axis, pretty small, right? What is it? Not even 400 kilometers of altitude. We propagate. That's already there. This comes default. Let's see how much time. 2 hours. 7,200 seconds. Okay. And I think that's the end of the story. So that we can visualize a little bit of that inside trajectory. That's probably, it's more than an orbital period. Yeah, I think so. And then there is a maneuver to the transfer ellipse. So here, so every time you have to solve for something, so again, my software here, this MCS that I'm creating, will have to solve for 2 maneuvers. The first burn to go to the transfer ellipse so that the apogee has the right distance, and that distance is the radius of the new trajectory you want, and then the second burn that circularizes, right? What we seen in class last time. So every time you have to solve for something, you add what is called the targeter sequence. So here, you go and insert a target sequence. Except I'm going to call it dV1 or delta V1, just because that's exactly what it's going to solve for. Okay. Inside this sequence, you have a maneuver. So these are all types defined for you. And we know we want an impulsive maneuver that is aligned to the velocity. That's what we're trying to solve for. It's a Hohmann transfer. So, it is impulsive. That's good. We are told to go for select thrust vector for attitude control. Here it is. And the Cartesian as the vector type is already there. VNC Earth thrust axis is already there. Just select the X. So by selecting these, I am basically telling STK this is going to be a maneuver only in the X velocity, because that's what is defined. That's the way it's defined. X velocity direction. That's all it's going to search for. Now, when you get to solving your own problems in a design class like next semester, again, you will have to be in charge of playing with these things to make it work. It's not so intuitive like going through a tutorial. Even when I did it myself with the students, we had to just try several cases until it worked. It's not something that works right away. But you have basically all the options here. You can choose continuous thrust, finite, which means basically continuous. You can give a thrust profile yourself. You can do all sorts of different things. But here we're sticking to a Hohmann transfer. Okay. I think that's all I needed to do, except what? Results. Where is it? Here it is. So what is this maneuver supposed to do? What does this maneuver obtain for me, the first delta V? Remember? Planet. I'm starting from this orbit. This is not to scale, absolutely not to scale. I'm saying that at some point I increase the velocity and I go on the transfer, right? Such that its apogee corresponds to the radius of the circle that eventually I want to obtain. So the goal of this dV1, delta V1, is taking me to the right apogee, right? That's what it needs to do. And the way you tell it to do so is this maneuver, the results that this maneuver has to give you is apogee. Or apoapsis, that's how it's called here. So altitude of apoapsis. So you go in there and select it, and it should be showing up. I don't know why it doesn't. Okay, just double click, I guess. It's nice when the buttons disappear on you. I click 3 times. It will eventually go away, hopefully. Nope. Okay. Sorry, it's frozen. Any ideas? All right. Please go away. Let's do it again. Oh, it's there. Okay. Let's assume that it will stay there. Now, you go back to the targeter. So this is the higher level targeter sequence, is what is going to iterate on that maneuver that I've defined that way, aligned to the velocity vector, until it finds the right solution or the right amount of delta V in this case, because I told it you can only go with the velocity vector, plus or minus. Using this differential corrector, basically is iterating, doing several simulations until you find the one delta V that gives you the apogee within a certain tolerance that you want. So I'm going to go inside the properties of this sequencer, target sequence, and select control parameter is the impulsive maneuver in Cartesian on the x-axis. I selected, I know that you probably don't even see it, but I checked that box up there so that this differential corrector, this numerical solver, knows it can change that value several times until it finds hopefully the right one. And I believe I'm also given that the max step that they want is 0.3 kilometers per second. This is how fine you want to go each time. It's going to try, I don't know, 0 delta V, 0.3, 0.6, 0.9, plus, minus. So it depends on how much you want to wait, how much time you want to wait. And also, he has to give me something in return. And the one thing I want in return is an equality constraint. I want the altitude of apoapsis to be not 0. I want it to be 42,000, let's see, 40, we have 5 minutes. We can finish it next time for sure, but let's use these 5 minutes. So this is the goal value that I want the corrector to obtain. Max step is 0.3. What else do they want? This is the tolerance. I don't think they're asking me to change it. 0.1 kilometers. It's pretty good. Okay. And then you make sure that you're going to run the active profiles, which is this, that is going to iterate. And that's the first maneuver. And I do believe that if I run this, it should show me something before I actually complete the maneuver. See? Here it is. Somewhere, it should show me what happened. I don't know what it is. Let's close this one. Here it is. So this is just the first maneuver. Okay, I've solved for the first delta V. And it's telling me here that it reached basically the desired apogee. I wanted 42,238, and it did achieve that within the tolerance. The difference is definitely below the tolerance in just 13 iterations, not 3, I'm sorry. And that's the delta V value that he found. Positive, of course. If the goal had been to go into an inner circle, I would have expected a minus in front of that, okay? Because it's a negative delta V. The one thing that I probably didn't do is give some colors to whatever is happening here. Yeah, well, because I don't have the propagate segment, that's why. So what this has done is has solved for the delta V, but it's not showing me that ellipse because I have to add the transfer ellipse because I have to add that. So let's go back into the satellite. So here, after I'm done with the maneuver, I propagate after the target sequence. So this is outside the target sequence. I don't have to solve for this. I just do a propagate sequence. You can change the color of this so that in 3D you're going to look at a different color, and you can clearly see the differences. So that was green, let's say yellow. And let's see, how long do I propagate for? Actually, I tell it when to stop. No. I want to propagate for half an orbital period, right? That's what you do on your transfer ellipse, right? Maneuver, you are a perigee of the transfer ellipse, you go all the way to apogee, and then you do the second delta V. So I want to tell it how to do that. Transfer to apogee. First of all, you can change the name of this to something that makes sense. The stop condition here, I'm going to erase this one. I don't like this one. Well, actually, you need to add a new one first. Stop condition. Do you see apogee or apoapsis? Yeah, right there. Thank you. I don't need this. I believe that's all I need to tell it so that it does propagate whatever happens after the maneuver, and it stops at apoapsis. Let's see. Yeah, I solved again everything. Here it is. So this is what I've solved for so far. You can imagine what happens at the apoapsis now. You're going to, I'm sorry, this is terrible. Can you see it? I don't know if I can make it brighter than this. But supposedly you have the green trajectory, which was your initial parking orbit. The delta V occurred somewhere here, and then you transferred into this ellipse. And I told the simulation to stop, Astrogator to stop at the apogee. We'll stop there, and then there you add another target sequence with another delta V identical to what I've done before, where now your goal is what? What do you want to do there? So, for example, your target would be to drive E to 0. That is what I think they suggest you to do. So the next delta V will be solved by trying to match the condition, the equality constraint of E equals 0. So try to finish this for next time. All right.